So now I'm going to start the linear programming. The linear programming is a systematic way to solve any scientific problem. As I mentioned before, that operation research is used to make decision more robust. You can use operation research as a tool to make decision. So if we try to relate real life with operation research model, so we can translate the real decision making process into the operation research modeling. For example, in real life, whatever decision we take, we treat it as a decision variable in operation research model. And decision variable is unknown value that comes from the solution of these linear programming problems. Another component of decision making is goal or objective. However, in operation research model, we translate that goals or objective into the objective function. An objective function is a polynomial. As a function is has a power of 1, then we call it linear programming. If polynomial has power of 2, we call it quadratic programming. If a polynomial has higher order, we call it nonlinear programming. However, in this course, we will just focus on the linear programming model, in which we will assume that objective function is a linear equation or a polynomial of first order. In decision making process, issues or conflicts are handled using constraints. So in operation research, we call them constraints. Issues are problems that we face to solve a problem are referred as a constraint. However, some parameters, some factors on the basis of which we make decisions are translated into the parameters, such as cost. Cost is noun, demand is noun. Any noun values are considered parameter in the optimization model or operation research model. So now we are going to start linear programming. A linear programming is a decision making approach that uses a linear function and set of linear constraints to solve the management problem. As I mentioned before, a linear programming has primarily 4 components. And yes, there is another component, we call it sets, that I will explain in upcoming sessions. The first component is a parameter, which are noun values on the basis of which we make decision. For example, if you're going to buy a car, so we have a different cars and they have their different prices. So we choose the car which is uh, which has least value. Decision variables are unknown that we need to calculate from the model. Objective function can be either of maximization or minimization. Okay, and constraints are the problems or issues that we deal while we make decisions. So to design an optimization problem or operational research problem, we have to keep in mind all of these components. In addition to that, we have another component, we call it sets. Let's say in your problem, if you are dealing different types of products, then that situation is modeled using sets. You are creating different scenarios, so different scenarios are modeled using sets. You're considering different routes, those routes are also modeled using those sets. So we will discuss in upcoming sessions. So here is a construction of different components used in linear programming model. As I mentioned before, that decision variables are the mathematical symbol that represent level of activity. For example, a manufacturing firm wants to produce radios, toaster, and clocks. So the number of units produced can be a decision variable that is unknown, which is based on the market demand, which is based on their production capacity. So based on the number of other factors, they will decide that how much of these product will be produced. So we can translate that problem or that set of the products into set of decision variables. Since we have a 3 product, so we translate those products into 3 decision variables. X1, which is a number of radios produced. X2 is a number of toasters produced. X3 is a number of clocks produced. Objective function. So objective function is a linear, nonlinear mathematical relationship that describes the objective of firm in terms of decision variable and parameter. In fact, it is a relationship between dependent variable and independent variable. For example, if we are going to optimize the total cost, so the total cost is a function of production. So total cost will depend on the function of different products being produced within the firm. So we can develop a relationship in the form of linear equation. So that linear equation is called objective function. And in this linear equation needs to be minimized or maximized. As in decision making process, while achieving some goals, we have to face some hurdles. To face some hurdles, we to keep the objective, and uh, we face some problems to achieve that goal. So if this is the situation, that situation is modeled using the model constraints. As I mentioned before, that we can classify constraints into two categories: equalities and inequalities. So basically, constraint is a relationship between available resources and the used resources. So there are two possibilities or three possibilities. Let's say we can say three possibilities. So the first possibility is that available resource is equal to the used resource. So this situation can be modeled using equality constraint. And in another case, available resource is more than the used resource. This is another case. An available case, available resources are less than the used resources. This is another case. So we can classify constraints into two categories: inequality constraint and equality constraints. I'll just give you an example of, let's say, for only 40 hours of labor may be available to produce reduced during production. So this situation can be modeled using constraint. Parameters. Parameters are given numerical values that are included in the objective function and constraint. For example, unit cost or sale price of radio, toaster, and clock. Demand of radio, toaster, and clock. So these are the some parameters. These are the some components of linear programming model. So now it's time to start a problem. It is time to solve a real case of business problem and solve that problem using uh, linear programming. So here is a example. We are starting with the maximization model example. Uh, Beaver Creek Pottery Company is a small craft operation run by a Native American tribal council. The company employs skilled artisans to produce clay bowls and mugs with authentic Native American design and colors. The two primary resources used by the company are special pottery clay and the skilled labor. Given these limited resources, company desires to know how many bowls and mugs to be produced each day in order to maximize the profit. So this is called product mix problem. So we want to know that how many mugs and bowls should be produced so that we can get the maximum profit. So here is the data. So you can see in the data set, let's say if they produce one bowl, they can get a profit of $40. If they produce one mug, they can get a profit of $50 per unit, and they have 120 pound of clay per day, and they have 40 labor hours per day. And to make one bowl, they use 4 pound per bowl, and they have only let's say only 1 hour is required to make one bowl. That is labor hour, 1 hour per unit. Same is for the mug. Mug requires 3 pounds of clay and 2 hours to make one unit. So now we will translate this entire situation into a mathematical problem. To convert this into the mathematical problem, we need to identify the decision variable, we need to identify the parameters, we need to identify, develop an objective function, and we need to develop the constraints. So I just summarize the data in the form of table. The best way to solve linear programming model is just to convert your data set in the form of table. Then it will be very easier for you to formulate the linear LP model. If you look at this, so the decision variable is number of bowls to be produced. X2 is another decision variable, which means number of mugs to be produced. And if you look at the first column, which shows the labor hours per unit per bowls, it takes 1 hour to produce one bowl. Okay, to produce one mug, it requires 2 hours. To produce one bowl, we need 4 pounds of clay. To produce one mug, we need 3 pounds of clay. And then we have availability of labor and clay in the last row of this table. So from here, from this table, we can easily develop the linear programming model. As I mentioned before, that we have 4 components of linear programming model. We started with the decision variable. So there are 2 decision variable: number of bowls to be produced, number of mugs to be produced. So this is an objective function, as we want to maximize the total cost of a total profit for producing both bowl and mugs, and we want to find a product mix of both bowls and mugs that would maximize the profit. So 40x1 plus 50x2 is objective function. So from here we can also develop the constraint. You can see the labor. We require 1 hour to produce bowl. We require 2 hours to produce a mug. So we can write a labor constraint as an inequality constraint, which shows that x1 plus 2x2 should be less than or equal to 40. So 40 is the total available labor hours, and on the left hand side of constraint shows the used labor hours. Same is true for the clay constraints. On the right hand side is the total availability of clay, and on the left hand side is the usage of the clay. So here is a final maximization, final model that needs to be solved. So to solve this problem, we use different methods such as simplex method, graphical method, branch and bound method, branch and cut method. But since this is a very simple problem and involves only 2 decision variables, so this type of problem can be solved using graphical method. Okay, so here is a problem. We have already formulated the problem, and now we will solve this problem using graphical method. To solve this problem using graphical method, we need to write a complete mathematical model in here, and then we can continue. So we have already formulated the problem in previous slides, so I will just directly write the problem here. Let's say we need to maximize z, that is an objective function, 40x1 plus 50 x2 subject to so now we have 2 types of constraint: labor constraint and uh, clay constraint. So let's write for clay constraint first. Then we have labor constraint. We can also write the labor constraint in here. And also we will add another constraint which is called non-negativity constraint, because the values of x1 and x2 shouldn't be 0. it should be greater than 0. It shouldn't be less than the 0. Okay, so now we will solve this problem using graphical method. Okay, so now I'm going to solve this problem using graphical method. So we will discuss the different steps of graphical method. So these are some steps for the graphical method. Now let's start with the graphical method. Graphical method is useful only when we have two decision variable, less than two decision variable. Variables as it involves some graphs. So that's why we cannot use this method for problems having more than two decision variables. So these are the some steps for graphical method. So the step one is construct the graph. For constraints, okay, so to construct the graph, we need points for straight lines. So let's say we have this graph in here. Say we have this graph, change it to the white color. Okay, and I represent this as x1, x-axis is x1, and y-axis is x2. Okay, since we have two constraints, so we need to construct the straight line. For straight line, at least we need 2 points. So here we have two constraints, so I will make two boxes. Call it x1, and this is x2. Then I will make another box. Again, I will call it x1 and x2. So I will go back to the constraints, and now in this first step, we will assume that all inequalities or equality constraints are equality, and then we will look at the points. So let's say we have 4x1 plus 3x2 should be equal to 120. 4x1 plus 3x2 should be equal to 120. And then we have 1x1 plus 2x2 should be equal to 40. Okay, so now to get the points, let's say I'll just choose different color for this. Maybe let's say I choose this one. Let's say x1 is equals to 0. If we put value of x equals to 0, then we can get the value of x2, 120 divided by 3, that is 40. So we got a point A, call it point A, 0 and 40. And from here, let's say if I put value of x2 equals to 0, and then from here I can get another point, let's say 4. So a value of x1 will be 30. So from here we get another point, I call it point B. 30 and 0. Okay, so I will repeat the same procedure for this equation as well. I put value of x1 equals to 0. So value of x2 is equals to 20. And if I put value of x2 equal to 0, and this will be equal to 40. So from here we can do the scaling. Let's say it's 10, 20, 30, and 40. 10, 20, 30, and 40. Okay, so from here, we got other points. I call it point C, which is 2, 20, and I call this point as a D, 40, and 0. Okay, so now I will construct the line for these points. If we combine these points, we will get a line for this equation. If we combine this point, we will get a line for this equation. So I will be choosing just different color for both equation. Let's say I choose this color for equation 1. So our first point is A, which shows A and 40. So on y-axis it is 40. We call it point A. A is 0 and 40. Similarly, we have B. B is on x-axis, this point. So I call it B, which is 30 and 0. So simply what we will do, we can connect these points with a straight line. So this line shows the equation for 4x1 plus 3x2 is equals to 120. And we will repeat the same thing with this equation as well. So here we need some points. Let's say okay, I choose this for this equation. So C point is 0 and 20. So here maybe, yeah. So this is point C, 0 and 20. And then we have another point D, which is 40 and 0. 40 in here. X1 is 40 and X2 is 0. Maybe this point, yeah. I call it point D, which is 40 and 0. And now we will connect these points. So this line is for this equation, which is x1 plus 2x2 is equals to 40. Okay, so from here we can see that we have found the points. So here is a point of intersection. Okay, so we need the value of this point of intersection, and to get the value of point of this intersection, we will solve these equations simultaneously. Let's say we have 4x1 plus 3x2 is equals to 120, and then we have another equation, x1 plus 2x2 is equal to 40. So you can use any method. Let's say I'm going for the substitution method. I call it equation 1 and I call it equation 2. So according to the substitution method, it will be 40 minus 2x2. This is equation 3, and from equation 3, if we put the value into the equation 1, from equation 1, let's say from equation 3, we put value of x1 into equation 1. So from here 4 into 40 minus 2x2 is equals to 120. So we can simply solve 160. 8x2 is equals to 120. So we can write minus 8x2 is equals to 120 minus 160. It shows minus 8x2 is equals to minus 40. So from here we can find out that value of x2 is 5, and if we put the value of 5 x2 is 5, so if we put value of 5 in equation 2, so from here we can find out value of x1, that is 2 into 5 is equals to 40. So from here, and x1 is 30. So we get this point, we call this point E, which is called 30 and 5. Okay, so next step is to identify the feasible region. So I say step number 2 is identify feasible region. Okay, so to identify the feasible region, we use these constraints. Let's say, let's check the feasible region for clay constraints. So let's check the different points and we will see whether these points justify the constraint or not. Let's say, let's take an example of clay constraint. Let's say this constraint, let's say pick a random point 40 and 40. Let's say somewhere in here. So if I put value of 40 here and 40 here, you will see that this constraint will be violated. So it means that this area is not valid for this area. The area on the right hand side of constraint is not feasible. So if we put, let's say I put value 10 10. So if I put value of x1 equals to 10 and value of x2 equals to 10, and then we will check the total value on left hand side will be less than 120. So it means that area under this curve, area under the line is a feasible region. So I treat it as a feasible region. So this area under the curve is feasible region. The same is true for the labor constraint, because it is again less than constraint, and point region under this line is considered as a feasible region. So this is feasible region. I just shared it. So simply we shared the feasible region. Okay, so in order to check that which point is optimal, we will check all these corner point for objective function. Okay, let's say we have objective function z. So I will check the objective function value at point A. At point A, we have these values 40 into on x-axis x1 is 0 plus 50, and on y-axis it is 40. So answer is 2000. Now we will evaluate another point, point B. Point B, yeah, it is in feasible region. So which is 30, 40 into 30 plus 0 into 50 into 0. So we get 1200. Since this point D is not infeasible, so we will not evaluate. So we don't need this point. you will evaluate only those points which are in feasible region. So in this case, even we don't need A. Yes, that's my mistake. We don't need A. We don't need that. So we have point B, point C. We will evaluate point C, ZC, which is 40 into 0 plus 50 into 20, so which is 1000. And then we have point E, which is again at in the feasible region, so we can evaluate ZC. ZE is 30 into 40 plus 50 into 5, so that is 1200 250. So if we add these values, so answer will be 1350. Now from here you can see that which one is maximum. So in this case, this point C has the highest value, this one. So we call this point E as an optimal point. And at this optimal point, we have value of Z equals to 350. And the value of X1 is equals to 30. And value of X2 is equals to 5. So this is the solution to the linear programming model, which means that if the company will be producing 30 bowls and 5 mugs, they can get the maximum profit of $1,350. That's all.